we are going to look at one last way of approximating the area under a curve without actually being able to find the exact area. So 5.5 is called the trapezoid rule, and instead of using rectangles, basically we're just using trapezoids to find the area under a curve. A trapezoid is a more effective method, as you might be able to imagine, rather than a rectangle. For example, if we look at y equals x squared, the picture drawn is going from 0 to 1, and I have 4 equal partitions. So how could we draw shapes under this curve to improve our estimate rather than using rectangles? I'm just going to go through this pretty quickly. Instead of using rectangles, we could connect each of these lengths using straight lines, and we have 4 trapezoids. And the tops of these trapezoids follow along the curve pretty well, much better than rectangles do. So again, when I connect those 2 lines, what shape do I get? I get 4 trapezoids. Okay, so same example, we have x squared using 4 equal partitions from 0 to 1. So the method here is to find the area of each trapezoid and add them all up to get another approximation of the area under the curve. So we have the area of a trapezoid, which we can also write as b1 plus b2 divided by 2 times h. It's the same equation, just written a little differently. So in this example, or in all situations where we're finding the area under a curve between the curve and the x-axis, using trapezoids, the height is actually going to be delta x. So if you're having a hard time imagining that, imagine that I take this trapezoid right here and turn it on its side. I'll draw it out for you. So something like this. So I just turned it to the right 90 degrees. This side right here is my delta x. This is my b1, and this here is my b2. So the height of this trapezoid is delta x, and that's how we're going to be using it in our equation. Instead of saying height, we are going to say delta x. So let's look at, without using an equation or without using an algorithm or anything like that, we can find the area of our trapezoids, just calculating them one by one. So in this example, each of our delta x's, so the height in each of these trapezoids right here is going to be 0.25 or 1/4. We can see we're going from 0 to 1/4. Then our next delta x is 1/4 to 1/2, and so on. So our first trapezoid, we're going to be taking the area of this tiny one to begin with here. And this is actually a triangle, not a trapezoid, so that will reflect in our equation. So right here, the area of our first trapezoid, we have the sum of our bases, which our bases in these equations are going to be f of xi minus 1 plus f of xi. So our x's are these values that we're plugging in to our f of x. So in this example, we're plugging them into x squared, and we're plugging in the first value, the first base, and the second base. So over here, our f of 0 is 0, and our f of 0.25 is over here, it's 0.0625, and we're taking our delta x, which is 0.25, which we said was the height of each trapezoid, and dividing that by 1/2, which is just a part of our equation for the area. So we do that, we get the area of that first trapezoid, it's very small, and then we have to continue this process for the other 3 trapezoids in this picture. So we do that, we calculate our 4 areas, and we add them all up, and we get 0.34375, which is an approximation of the area under this curve. So we just reviewed the area of the trapezoid is B1 plus B2 divided by 2 times H. And we said that we are going to say delta X is actually H. Oops, sorry. And our B1 and B2 are going to be f of x sub I minus 1 and f of x sub I. So those are the two bases. We are going to be added up. Notice how they are in order, just x minus 1, I minus 1 and I. So those are going to be the heights of two bases right next to each other. So again, we're estimating the area under the curve using this method. So we are estimating the integral from a to b of f of x dx using this trapezoid method, which we can write as, so it's approximately the sum of all of our areas. So the sum from I equals 1 to n of the areas of these trapezoids. So rewriting this equation with these variables, we get f of x sub I minus 1 plus f of x sub I divided by 2 times delta x. So you guys may be able to see where this is going. In our previous examples, we had said that as we get more and more accurate, our delta x becomes dx. So we may be able to see how this formula slowly translates into our actual integral. So between this step and the actual formula, there's a couple steps in the proof which I'm not going to write out here, but I will post a copy of my notes online containing that proof if you would like to go back and look. But in the end, this approximation, we are able to factor out our 2 and our 1/2 and our delta x because those are both going to be constants. So we're able to factor them out to the beginning of the equation. So we have delta x divided by 2. And we are going to multiply that by the sum of all of our bases. Now, the formula I'll write out first and then I'll explain it. So it's f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2. We continue on like that until we get 2 times f of x sub n minus 1. And then notice when we get all the way to f of n, sorry, don't copy that down. When we get all the way to f of n, we only take that into our equation one time. So our first term, f of x sub 0, and our last term, f of x sub n, we only are adding in one time, but all of our other, remember these are the base lengths that we have, are factored in twice. Now this is because, I'm going to go back a couple slides, when we're adding up our areas, each of these base lengths, the f of 1/4, f of 1/2, and f of 3/4, are used in two different trapezoids. So we can see here, our f of 1/4 is used here, and it's also used here, and f of 0.5 is used here, and it's also used here. So two of these lengths, 2 times these lengths, are used in our sum. But if we look here at our first length is f of 0 is our first base length, that's only used once, and our last base length is f of 1, which is also only used once. So that is where this formula comes from. In the end, we do 2 of each base length, except for the first and the last. So this here is our formula for finding the area under the curve approximated by the trapezoid method. One thing to note about this is this method only works, this equation only works when this delta x is constant. So we factored out all these delta x's from this equation because we were assuming that the length of each, or the height of each trapezoid was the same. So again, this specific equation only works when delta x is constant. So again, our first example, delta x was 1/4 for every trapezoid. So we are allowed to factor that 1/4 out. Okay. So here is that trapezoid rule written out, the final equation. And one other thing to note, this can also be found, the area using the trapezoid method, by adding up our LRAM, R, and RRAM divided by 2. So the average between LRAM and RRAM. So that's just one thing to note. Depending on what kind of data you're given, one method may be easier than the other. So that just depends. So if you're choosing to do this way, if you were given LRAM and RRAM, it would be easier just to take the average. But using the trapezoid method only requires one calculation, where LRAM and RRAM both require one, and you'd have to do both. So let's look at this data we're given, and let's use the trapezoid method. To approximate the area under curve of this function, which we're going to call f of x. So what we're actually looking for is the integral, we're going to say from a to b, of f of x dx, and we're going to approximate it. So we can look up our x's are 2, 3, 4, 5, 6, 7, 8. So we can see that our delta x is just 1 between each trapezoid. So we can use that formula that we just went over with a constant delta x. So my integral right here, integral from a to b of f of x dx, is approximately my delta x over 2 times, so starting with my f of 2 right here, f of 2 plus, now I start taking each base length twice, 2 times f of 3 plus 2 times f of 4. I'm going to keep going with this until I get to my last x value, which is f of 8, which remember I only add in one time. So I have these values right here, and I can plug in my delta x, which is 1, and each of my f of x values are given in this data set. So I'm just going to plug in all the values that I need. So I have 1/2 times 16, my f of 2, plus 2 times 19, plus 2 times 17, plus, keep going, 2 times f of 5, 2 times f of 6, 2 times f of 7, plus 1 time only f of 8, which is 20. So I'm going to add up all these values, multiply by 1/2, and what I get is 97, which is approximately the area under the curve of f of x from a to b. And in this case, our a is 2 and b is 8. Okay, so going back to our first example of x squared, we were asked to find the area under x squared from 0 to 1 in 4 trapezoids. So remember, our delta x is given by b minus a over n. So we're going from 0 to 1. So my b minus a is 1 minus 0, and we had 4 trapezoids, so over n. And you remember we used in that first example 0.25 in each of our calculations. So if we were going to use 5 trapezoids instead, the only thing that changes is our delta x. and our b minus a is still the same because we're still going from 0 to 1. However, our n is now 5, so our delta x is now 0.2. So that's the only thing that changes about changing the number of trapezoids, as long as they are the same height. So as long as the partition length is the same. So we're assuming that the partition length is still 0.20 for each trapezoid. Okay, so moving away from that kind of example, here we're given square root of x, and we're asked to approximate the area using trapezoids. So instead of using trapezoids of equal length, we have decided we are going to just use 3 trapezoids, and notice that they all have different lengths. This first one has height 1, the second one has height 3, and this third one has height 5. So we can now go back to using our method, which started with whatever the sum of delta x over 2, blah, 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 because our delta x is different every time. So we had this value of all of our bases added up, and we're multiplying them all by the same delta x, but that's no longer going to give us an accurate area of the trapezoid. So in this example, we need to calculate all of our areas separately and add them up. So our integral of f of x dx is going to be 3 areas just added up. No specific formula to find that value. And again, in this last example, we're given data just like we were in the previous example, but you have to notice delta x is different over every data point. So again, we have to calculate the area of each trapezoid separately and add them up. And if we go back to the beginning, when we were deriving that equation, we can use this formula right here, just the simple area of a trapezoid by itself, using delta x as our height every time. We can change what delta x is every time and just keep adding up those areas. So to sum this up, notice just one more time, in the last 2 questions, the partitions were not uniform, so you need to know how to do both methods. So at this point, we've gone over 4 approximations. We did LRAM, RRAM, NRAM, and the trapezoid method. Again, I'll reiterate, when we were using geometric shapes like rectangles and semicircles to calculate those areas, we were calculating the exact area under the curve because we knew what kind of geometric shapes those curves actually were. And lastly, there will be no homework in this section. You can go back and try those last 2 slides since I didn't really calculate the area under those curves if you would like extra practice, but I think all the stuff we did with MRAM and RRAM and LRAM is a decent amount of practice. We're just using different shapes to find these areas.